Okay, so I think now it's started, right? Okay, so now,
Sir, sir, I have a doubt, sir.
yeah, yeah, go
Uh,
ahead, go ahead.
Sir, I am studying in second semester this year only. So this course is good for me, or it's above my
No,
semester?
no, no, it's good for you, no issue, right? So I am going to teach from the very basics. So if you are a, let's say, mechanical engineer, then definitely it's always good for you, right? So
Okay,
don't.
thank you, sir. Thank you.
So now the second classification I can make on the basis of nature of constraint, right? On the basis of nature of mechanical constraint. So under this category, you can classify a kinematic pair into two types, right? So under this category, one will be called as closed pair, right? And another one will be called as unclosed pair, right? So what is a closed pair? A closed pair is basically referred to as a kinematic pair in which the links they are held together mechanically. Okay, so by enclosing one link into the another. So I will come to this, like how what this definition is trying to convey. So now let us move to unclosed pair. So in unclosed pair, the links are not held mechanically. So the simple distinction between a closed and unclosed pair, that in one the links they are held together mechanically. So that means you are using the shape of links. That means one link it is going to be contained inside another link, right? Now in unclosed pair the links they are not held mechanically. So if they are not held mechanically, that means there must be some external force to hold them. Yeah, or you can say to bring these two links into contact with each other, right? So here the links they are not held mechanically but due to some external force. So due to some external force, so external force, a general external force which we use generally for mechanisms is a spring, or simply you can say force due to gravity. So let us try to understand this through this example. Let me just drag this figure somewhere here. So if you see this diagram, right? So in this diagram, you can see this is a cam and follower arrangement, right? So here you can see this line is tracing the shape of the follower, and this is your cam, right? So now this cam is fixed at this particular point, right? Or you can say this is going to rotate relative to this fixed point, right? So now you can see here the follower, it is enclosing the cam. That means they are being held due to the mechanical shape of this cam and follower, right? Now this type of arrangement, this is referred to as closed pair. Now if you come to this here, you don't see any such arrangement. So here if you consider this cam as link 1 and this follower as link 2, so here you can see that these two they are in contact due to force of gravity, correct? So the contact between two links is only due to force of gravity. So such pair are called as open pair, right? So generally, this is also referred to as form closed, right? So, and this one, this is also referred to as force closed, right? So although it is an open pair, but since we are using some external force or the force of gravity, gravitational force to maintain the contact between these two links. So sometimes we refer to this as open pair as or unclosed pair as force closed also, right? So just remember this. So now let's go to another one. So this is a slightly important. Now further we can classify the kinematic pair on the basis of relative motion between two links. So this is very important, right? So just focus here. So the first under this category, so the first classification, the first type is sliding pair. So can anyone just guess by the name of this kinematic pair, that is sliding kinematic pair? So how these two links, let's say like a pair of links are there. So how these two links they are going to move relative to each other? Can anyone guess that if there is a sliding kinematic pair,
Sir,
right?
so two links will be having sliding motion relative to
Correct.
each other.
Right? So it's very easy. So by the name, again, you can very easily infer that here, what will happen? The two links, they will have sliding motion relative to each other. So in such cases, you can refer to this kinematic pair as sliding pair. Okay. So now one more important thing. Generally, we call this a sliding pair as prismatic pair also. Right. So just remember, so we call this sliding pair by different names. Let's say like one more is prismatic pair, right? So a simple example for this is, let's say if you consider, very easy, if you simply consider a rectangular rod moving inside a rectangular hole. So you can very easily see here in this case what is going to happen. In this case, these only translation or sliding motion will be permitted between the two links. So let's say like here you can see one example of a prismatic pair. So this is your rectangular rod, right? And this is your rectangular hole. So let me call this as link 1 and this is as link 2, right? So you can see that there will be only translatory motion between these two links, that is link 1 and 2. Now a very important thing, degree of freedom. So can anyone just define what is degree of freedom? What is the definition of degree of freedom? Can anyone define?
The number of directions in which a body can move.
Okay, so the number of directions in which a body can move. So anybody else? So many a
Number
times,
number of independent relative motions.
right, correct, right? So one is like one of the students said like okay, the number of relative motions. So basically, you can very in very simple words you can define degree of freedom as number of independent coordinates. Remember, number of independent coordinates needed to specify. So both the definitions are correct, which was given by the students. So it is just more refined definition. That is the number of independent coordinates needed to specify the relative motion between two links, right? So now here, if I ask you that what is the degree of freedom of this prismatic joint? So can anyone answer? So what is the
One.
degree of freedom? So it will be 1. So why 1? Because you will need only one coordinate, that is delta x. Let's say like this link to it is moving relative to the link through a displacement delta x. So you can define the motion of these two links, relative motion between these two links through only one coordinate, which is delta x, right? So here, this delta x, just remember, this delta x is generally referred to as pair variable, right? So the pair variable is a single variable which is delta x. So the degree of freedom is equal to 1. Right? Now let us move to another pair, another kinematic pair. So this is generally referred to as turning pair, or more popularly it is called as revolute pair. So just remember this name is quite popular, that is revolute pair, right? So here, as the name suggests, here the two links have simply turning motion, or you can simply say rotating motion relative to each other. So one of the example for this is simply a circular shaft inside a bearing. So this is a very simple example, right? So let us try to understand this through the diagram. So if you see this diagram, right? If you see this diagram, so you can see that this is one link. Let's say call this as link 1. So this is basically a collared shaft. Collared shaft means there are collars at the end of this shaft. So these two flanges which you are seeing here, these are generally referred to as collars, right? So now this collar shaft, it is situated inside a bearing. So let us call this link 2, and this is your bearing, right? And this is your shaft. So it's very easy to guess. Now here, since this shaft is collared, right? So the translatory motion, it will be restricted. So the only motion which is allowed here, it is the rotary motion of this shaft, that is link 1 relative to the link 2, right? So such kind of joint is called as, right, revolute joint. So now just tell me here the pair variable. What is the pair variable in this case? So it's very simple. The pair variable you can define by, let's say, delta theta or simply theta, right? So here theta is the pair variable, and what will be the degree of freedom? So just tell me what will be the degree of freedom for a turning pair?
1.
Obviously. So now here you can define the rotary motion only through a single coordinate, that is theta or delta theta you can say, right? So the degree of freedom in this case will again be equal to 1. Now coming to the next kinematic pair. Okay. So this is generally called as cylindrical pair. Now in a cylindrical pair, this is very important. The two links have translatory as well as rotary motion, right, relative to each other. So this is very important. Now in this case, what is going to happen? In this case, the two links, they are going to have a translatory as well as a rotary motion, right? So a very simple example, you can simply say cylindrical bar or cylindrical rod inside a cylindrical hole, right? So a very simple example you can take to understand this, right? So now just go back to this diagram, right? Now these two diagrams, if you observe this revolute and this cylindrical joint, they are almost similar. But what we did, we just removed the collars on the shaft. Fine. So here if you see, we don't provide any collars, right? So now in this case, what is going to happen? If we remove the collars, this shaft, okay, so let me call this as link 2, link 1, right? So it is obvious this shaft, or you can say cylindrical rod, this is free to translate in this direction, right? So it is going to translate as well as it is going to rotate, right? So very important thing here. So now just tell me how many pair variables are there in this case?
2.
2. So which two pair
Two.
variables?
Delta x and
Delta x
theta.
and
Delta x
theta.
and delta theta. Now, very important question I am going to ask you now. Are these two coordinates, x and theta, are they independent of each other? So just see here. So are they independent of each other? So
Yes.
Yes, sir.
Yes.
Yes.
Yes, sir.
Yes,
good.
sir.
Yes, that means these two are independent variables. That's why we are calling them as pair variables. And now the degree of freedom for this will be equal to how much?
Two.
Two.
2.
2. Very good. Right. So this is called as cylindrical pair. Right? So why it is necessary to study this kinematic pairs? Because later on you will see that in a mechanism, all the links they are connected by this kinematic pairs, and finally the degree of freedom of the entire mechanism it is decided by the degree of the freedom of the individual kinematic pairs. So that's why it becomes necessary to study this kinematic pairs, right? So now after cylindrical pair, we have spherical pair. So this is something very interesting. Spherical pair. So now in this case, what is going to happen? In this case, one link in the form of a sphere. So this is a very important kind of like a pair. So which you encounter actually in your day-to-day life every day, right? So in this case, one link in the form of a sphere, it turns, or you can simply say revolves, rotates, whatever you wish. So it turns inside a fixed link, right? So now, can you give me some example of such situation? So let us consider the case of human body, right?
Shoulder.
Shoulder, right? So
Joints.
very good. So in shoulder, which joint you have? Just tell me, like, if you remember the name of that joint, you might have
Lock.
read it.
Ball and
Ball
socket
and
joint.
socket joint.
Very good. So spherical pair is simply your ball and socket joint, right? So ball and socket joint. Now, here in this case, the pair variables, let us talk about pair variables, right? So can anyone just tell me what is the degree of freedom of a ball and socket joint?
2.
Is it 2?
3.
Sir,
One.
three. Sir, three.
Infinite.
Or 3? So very good.
Three.
So generally the degree of freedom of a ball and socket joint is 3. And the coordinates, they are basically represented in a polar coordinate system. Rather than Cartesian coordinate, we go for a polar coordinate system to represent a ball and socket joint. So let us see how, right? So if you see this, if you clearly see this diagram, generally to represent a ball and socket joint, what we take the axis. So let's say, let me call the center of this, okay, this thing as, let's say O, and let's say, let me represent this axis as A, right? So this is your fixed link. On this side, this is your fixed link. Let me call this as 1, and let me call this link as 2, right? And now the axis of this link, let us say it is OA, right? So in this case, what is going to happen if you take a Cartesian coordinate system? So if you observe this delta phi and delta psi, right? Very important. So generally this delta phi and delta psi, right? They represent they represent the position of axis OA, right? And now this delta theta, right? This delta theta which you are seeing here, right? So this very important, very carefully watch this. So if you move this OA, right, if you move this OA inside this fixed link, rotate this, then generally this delta phi and delta psi, they will represent the position of this axis, okay, relative to this Cartesian coordinate system, right? And the delta theta, it is going to represent the rotation of axis OA, right? So this link 1, this link, this link 2, it is rotating about its own axis, right? OA. So one coordinate, that is delta theta, it is required to represent the rotation of this axis, right? So two coordinates, delta phi psi, they represent position, delta theta represent rotation. So in this way, we refer that, okay, the degree of freedom of this spherical pair or a ball and socket joint is 3, correct? Now let us move to another type of joint. So this is also very important. helical pair. Helical pair. Okay. So here again, two links will have translational as well as, so let me introduce this word, right? So here again the two links will have relative translational as well as rotational motion, right? So very important thing. So let me ask you just, so if this is the case, then what is the difference between a cylindrical pair and a helical pair? Can anyone guess?
It
They
is
are
not
not, they are
independent of
dependent,
the
they are
motion.
dependent.
They are dependent. Very good, right? So here if you observe these two coordinates, right, these two coordinates delta x, delta theta, they are independent of each other. But in this case, what will happen? But the two motions, right, two motions are dependent. Okay, so now let me ask you one more thing. Why do we use this word helical? So can anyone guess why do we use this word helical? See, somewhere this is suggesting that one link will be in the form of helix, correct? So from there it is deriving this name as helical pair. So can you give me some example for a helical pair? So where you
Screw,
yeah, go ahead.
sir, the screw we put in the object.
Correct, right? So very simple example of a helical pair is simply lead screw and nut arrangement, correct? So here if you observe, so this is your helical joint. So in this case, when you turn the screw, right? So this is your screw and this is your nut. So we all know when we turn the screw, so this nut is going to translate in this direction. But what happens, this delta x and this delta theta, in this case, they both are dependent upon each other. So generally they are related through this relation, right? That is, in this case, the pair variables. So in this case, either you use delta x or delta theta, right? And generally these two pair variables, they are related by this relation, right? So here this L is generally called as lead of screw, correct? So now the degree of freedom of helical pair will be equal to how much?
One.
Obviously, so either you use delta x or you use delta theta, so the degree of freedom is equal to 1, right? Now, the last kinematic pair is planar pair, right? So now in a planar pair, right? So let me quickly write down now two translations and one rotation, right? So I'm writing down this in very short. That means two translations and one rotation between two links, right? Now, just try to understand this. So if you see this, right? So this is generally also called as flat joint or F joint. So if you see this diagram very carefully, so let me call this surface, right? So this surface as link 1. And let me call this rectangular bar over this surface as link 2, right? So now if you talk of pair variables, so if you observe this rectangular bar, it is free to translate along this direction. So if let's say like I establish a coordinate system z, then this is your x and this is your y. So this rectangular bar, it is free to translate along x direction, along y direction, and at the same time it is free to turn around this z axis, right? So here two translations, that is along x and along y, and one rotation, that is about z axis, that is possible, right? So here if you talk the pair variables, so just tell me how many pair variables will be there in this case?
3.
3.
3.
So which one? Delta x, delta y, and delta phi. Right. So the degree of freedom of a planar pair is how much? Equal to
3. 3.
3. Right. So because here these three coordinates, they are independent. Right. So the degree of freedom of a planar pair will be equal to 3. So fine. Here we stop the discussion on kinematic pair. So let us just move to types of kinematic pairs, or you can say the types of joints, right? So this is something very important. This also plays a crucial role while determining the degree of freedom of an entire mechanism, right? So let us understand this. What is this? Binary joint. Okay. So binary joint, as the name suggests, that if it is a binary joint or a binary kinematic pair, then two links, right? Two links are connected at the joint. Very easy, right? So this is your let's say connection. So just this is a simple schematic representation. Always remember the actual shape of connection, it might differ. So let's say like if you use a nut and bolt or something like that, but just a schematic representation of that, let's say like links and kinematic pairs, we use such diagrams, right? So in this case, this straight line which you are seeing here, let me call this as, let's say, link 1. This is your link 2. Now these two links are connected at this particular joint. So this is generally called as binary joint. Now similarly we can define ternary joint. So what will be a ternary joint? Just tell me quickly.
Three links are
3
joined at the
links.
next.
Right, so how many links will be connected? 3 links
3.
connected, right? So now this will be your ternary joint, right? So this is link 1, this is link 2, this is link 3. So similarly, we can go ahead with quaternary joint, then penta, then hexa in a similar way, right? So if quaternary joint is there, then 4 links will be connected at the joint. So I think now it is clear to all of you. Now just remember, many times the students, they get confused between binary link and binary joint. So let's say if a binary joint is there, then we are saying that 2 links will be connected at the joint. And if binary link is there, always remember, if a binary link is there, then we say that okay, it will have 2 connections, right? Or you can say one link, it will be connected to 2 other links, right? That is link 1, it is connected to link 2 and link 3. So never get confused between a binary link and a binary joint. So let's say like if I ask you how many connections will be there in a binary link, so you will say that there will be 2 connections, right? Or 2 joints in a binary link. But if I ask you how many joint will be present in a binary joint, then you have to say that okay, only one binary joint will be present there, right? So just don't get confused between binary link and binary joint. Okay, so let us move ahead and let us talk about a very interesting thing, right? Very interesting thing which many a times most of the student miss, and many a times such kind of questions they are asked in gate examination, right? But they are, since the students they get confused with so many definition and let's say like terminologies. So this is very important part. So I just need that you all focus on this part, right? So now let me talk about kinematic chain. What is a kinematic chain? Okay. So now after defining links, after defining, let's say like mechanism, machine, all these things. Now let us come to this. What is a kinematic chain? So a kinematic chain is nothing. A kinematic chain, it is an assembly of links, right? Connected by kinematic pairs. So this is very obvious. So if you talk of chain, so chain is nothing. So number of links, they are connected by kinematic pairs. Now this is very important. A kinematic chain, it can be classified into 2 types: closed kinematic chain and open kinematic chain, right? So it's very easy to guess that what is a closed kinematic chain. A closed kinematic chain, as the name suggests, that these links, they will form a closed loop, right? So the links will form a closed loop, you can say, right? And here the links or assembly of links, it will remain open, right? So this is very easy. Now let me ask you one thing. If I have to form a closed kinematic chain, so what is the minimum number of links which I need? Can anyone guess? Did
3.
you got my question?
3, sir.
Okay. So that means if you have to form a closed kinematic chain, so the minimum number of links which you need is 3. Very obvious. So now you can very easily see this thing here. So let's say this is my link 1, right? Now again, there is a kinematic pair at this point. Then again, this link 1 and 2, they are connected through this kinematic pair. And finally, there will be one more link, that is link 3. Right? So the minimum number of links which you need to form a closed kinematic chain is 3, correct? So now if you see this, if I call this closed kinematic chain as, let me refine this definition further. That means one link, one link should be connected to at least two other links. Then only we can say that the kinematic chain is a closed kinematic chain. So this is very easy to guess. So if you talk of link 1, so link 1, it is connected to link 2 and 3, right? If you talk of link 2, so link 2, it is connected to link 1 and link 3. If you talk of link 3, so link 3, it is connected to link 1 and link 2. So if you see a single link, it is connected to at least two other links. Then only we can say that a kinematic chain will be a closed kinematic chain. Remember, just remember this, right? So now you can, let's say, like increase the number of links, right? Now you can see every link, this link connected to these two, this link connected to these two, right? So every single link, it is connected to two other links to form the closed kinematic chain. Now this is very important. Let us define mechanism in terms of closed kinematic chain, right? So let us define a mechanism in terms of closed kinematic chain. So let me put another terminology for this, mechanism and linkage, right? So nowadays this mechanism and linkage, they both, these two words, they are both used interchangeably. Just remember. So if anybody says like linkage or mechanism, both are same thing, right? So now if one of the links of kinematic chain is fixed, right, to ground, or you can simply say that it is fixed, right, then that kinematic chain is referred to as mechanism, provided, so one of the links of kinematic chain, it must be fixed to ground, right, provided, this is very important, provided that the links possess or they have definite relative motions, right? So the motion of links, it should be definite relative to each other. So they cannot move in an arbitrary manner. If they are moving in a random, or let's say in an arbitrary fashion, then we cannot say that this will be a mechanism or a linkage. So two criteria should be satisfied. One is that the mechanism, okay, so to call a kinematic chain as a mechanism, first of all, one of the links of that kinematic chain, it should be fixed. And the second criteria, that the link should possess definite relative motions with respect to each other, right? So now, if you observe here, in a definition of kinematic chain also, I said like an assembly of links connected by kinematic pairs. So as soon as you connect two links by kinematic pairs, definitely they links, in this case also, the links have definite relative motions with respect to each other, right? So even for a kinematic chain also, the link, they should have a definite relative motion with respect to each other. So if this criteria is not satisfied, then we will not say that this is a kinematic chain or a mechanism, correct? So now, in other words, you can define a mechanism simply a closed. So this is very important definition, right? It's a closed kinematic chain in which one of the link is fixed, right? So this is a very important definition of a mechanism, which many a times, let's say, like is asked in interviews or gate examination, right? So in simple words, you can say, what is a mechanism? A mechanism is nothing. A mechanism is a closed kinematic chain in which one of the links is fixed, right? So now let me ask you this question. Can we call this open kinematic chain as a mechanism? So can a open kinematic chain, we call this as a mechanism? So if this is the definition of a mechanism, that a mechanism is a closed kinematic chain in which one of the link is fixed. So as soon as we call this as a
No,
kinematic chain,
no, we
so
can't
that
call
means,
it.
right. So that means the links, they are going to have definite relative motions with respect to each other, and definitely in that case we cannot call this open kinematic chain as a mechanism, right? So we cannot call this as a mechanism. So just tell me, can you give me some example? But means my point is, but it is not like that, that this open kinematic chains, they are not important. So they are also important, but we study these open kinematic chains in a different subject, not in this subject, right? So can anyone just guess? Can anyone just give me some example of an open kinematic chain? So can anyone just give me some example of an open kinematic chain? So, so okay, let me,
Hands, hand of
okay,
a human.
okay, fine, that is also correct, right? So if you take our arms, right? So our arms are also an open kinematic chain, right? So now you can see here, like this, you can consider this portion as link one, this as link two, then you can consider this hand as a link three, right? So this is open kinematic chain. Any other example? So nowadays we are like going for heavily for automation in industry,
JCBs,
right? So,
articulated robots.
right. So very good. So the best example for this is robot. So generally we study open kinematic chain in a different subject, which is called as robotics, right? So now let us come back to our original discussion, that is mechanism. So a closed kinematic chain with one of the link fixed is called as a mechanism, and these links, they are going to possess definite relative motions with respect to each other, right? Mechanism is also called as linkage, right? Now, beside this, we have another important definition which is called as structure. Structure, right? So before going to the definition of a structure, right, let me define this redundant kinematic chain. Redundant kinematic chain. So what is this? Right? So a redundant kinematic chain, what is going to happen? The links, or you can simply say the relative motion between the links is absent. That means we are referring to a series of links connected by kinematic pairs. But if this kinematic pairs, right, if this kinematic pairs, they don't have any relative motion between them, right, or the relative motion between the links is zero. So in that case, we call this as redundant kinematic chain. And now, if we fix one of the links of a redundant kinematic chain, right? Then it is called as a structure. Called as a structure. So let me give you an example for this. So generally we are referring, now always don't get confused. Generally we are referring to this as redundant kinematic chain, but you can assume that this is not a kinematic chain at all, right? But generally we refer this with some different name, which is redundant kinematic chain, because we know that if it has to be a kinematic chain, there must be some relative motion between the links, right? So, but since there is no relative motion between the links, we can refer that it is not a kinematic chain at all, or generally we refer to this as a with a different, let's say, like word, which is redundant kinematic chain. So if we fix one of the links of a redundant kinematic chain, then it becomes a structure. So let me give you one example. So it's very easy. Just take a series of three links, right, connected by some kinematic pairs. So maybe let's say like they are being connected by some revolute pair, R pair, right? So if you see this, so is it possible that, okay, is any motion is going to relative motion is going to exist between these links? So is it possible? No, right? So let's say I am taking the dimensions of these links in such a way that there is no relative motion between the links, right? So this will be generally referred to as redundant kinematic chain. Now what we do, right? So since there was no motion, relative motion between the links, but if you see here, can I consider this entire thing, right? So the entire combination of these three links as a single link, as a single ternary link. Can we consider this?
Yes.
Right? So if you remember, I said like for a ternary link, there must be three connections. So we can easily call this entire combination of three links, since there is no relative motion between the three links, right? Then we can refer to this as a single link, and this link will in this case called as ternary link. So what is my point? If you use this ternary link in a mechanism, it is free to move, right? In let's say like it is free to move in its entirety. That means that this combination of three links, they will move as a single rigid body, right? If you consider this in a mechanism. Now what we do, if we just fix one of the links, so the motion of this ternary link, it ceases, right? So in that case, it becomes a structure. So is it clear to all of you? Any doubt here?
Yes, sir. I have a doubt.
Yeah, yeah. Just
In ternary link, three links are joined at a connection, but here how? uh,
what? No, 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 no. That's why in the previous session I said to you that don't get confused between ternary link and ternary joint. In a ternary link, you will have a combination of three links, right? And you will have three connection points, right? But ternary joint is different. This is ternary link. Ternary joint, you will have three links connected at a particular joint, like this, right? So is it clear?
Yes,
Just
sir.
don't get confused between ternary
Sir,
link and ternary joint. Both are different, right?
sir,
Yeah.
sir, the wheels of a car would come into the mechanism, right? So like the rigid,
So the wheels
because
of
they
a
don't
car,
have relative move.
yeah. So see, the wheels of a car, they can come under, let's say, like a category of kinematic pair, right? So I won't say like they will form a like entire mechanism, but let's say like if you connect other arrangements, right? So let's say like if you connect some gearbox, some clutch, and somehow if you close this chain, right? So in any case, the chain should be closed, right? So I think it's possible to model a vehicle as a, let's say, like closed kinematic chain. So in that case, you can model this, let's say, like wheels as link one, and then let's say like two wheels as link one and two. Then in between, you can consider other links, let's say like clutch or gearbox or something like that. So it is possible, I think, to model this automobile as a closed kinematic chain, right? So the only thing you have to remember that the chain should be closed, right? So since here are wheels on front and back side, so I think it is possible to close the kinematic chain and form a mechanism for an automobile. So anything else? So this structure and redundant kinematic chain is this definition is clear? So what is a structure? Is it clear to all of you? Any doubt? Anybody? Okay, so shall I move ahead? So till this point, if any doubt. Okay, so shall I move ahead?
Yes,
Okay.
sir.
Okay, so now just to be very much focused, because now I'm going to discuss very important thing, right? So all these because let's say if you go for higher competitive exams or wherever, so nobody is going to ask you, let's say, like in too much depth, but the basics they are, should be must be very much clear. So all these, like which I am telling you, these are the basics of kinematics of machine. So this will be used everywhere, right? So see, for higher let's say like complex methods, complex technology, you can always refer to book, right? But as you move forward in your career, the basics should be clear. So even if you want to become a good engineer later on, right, nobody is going to ask you, everybody knows that you have a book, you can always refer to the book to see the complex methods and let's say like complex terminologies, whatever. But the basics, right, the basics should always be there in your mind. Then only you will be able to, let's say, like build something in ansys or in any other software, or design, let's say, like some machine, something like that, right? So now let us move to another important discussion. So generally, now we are going to discuss mobility of mechanisms. Now, till now, we discussed the mobility of kinematic pairs. Mobility, or you can simply say the movability. That means, simple words, mobility means how the links are going to move relative to each other. Relative to each other. Or in other simple words, right? The objective, the aim of studying this topic, mobility of mechanisms, is simply to determine the relative position of the links, like to get a feel or an idea that how the links they are going to move relatively to each other. That means what will be the relative position of the links at a particular instant of time, right? So now, generally, the mobility of a mechanism, it is expressed by degrees of freedom, right? So now you can see here the way to define the degree of freedom is almost the same. So there is a minor change when we in the definition when we refer to this in context to, let's say, like mechanism. So what is degree of freedom? So here number, you can define degree of freedom as number of independent coordinates needed, very important, needed to specify the configuration of a mechanism, right, at a particular instant of time. So we all know that the links in a mechanism, they are going to move with respect to time. They are going to change their position relative to time. So now the number of independent coordinates that are needed to specify the mechanism configuration at a particular instant, right? Or you can simply say, when I say configuration, that means relative position of links, right? So we are just interested to see the relative position of the links. So this will become more clear when we later on go for velocity analysis, displacement analysis, all these things, right? So right now we are just having an idea that if there is one input, then how the output link is going to behave, right? So now the degree of freedom, okay, after the definition, let us derive the relation. Let us go to another page. Right? So now we are interested to find out the relation. So let me define few things. So let n is equal to number of links in a mechanism. Now j, let j is equal to number of simple, right, simple kinematic pairs with 1 degree of freedom, right? So it will be simply either, let's say, like revolute pair or prismatic pair, right? Something like that. So just remember that n is the total number of links in a mechanism, right? And j is number of simple pairs. That means the pairs which have only 1 degree of freedom, right? So it could be a revolute pair or a simple prismatic pair. Then let's say h is equal to number of higher pairs, right? Now let us try to find out the degree of freedom of a planar mechanism, right? And let's say like f, capital F is the degree of freedom for the mechanism, right? So let us see how these are related, f, h, j, n, right? So let us try to find out this. Now first of all, we are going to talk about planar mechanism. Always remember, so we are not considering the case for spatial mechanism. So spatial mechanism means that the links, right, or the points on the links, they are going to move in all the 3 dimensions, that is x, y, and z. But here in a planar mechanism, right, remember the links will move either in a single plane or in parallel planes, right? So generally you can, the idea is that you can define the motion of the links of a mechanism in a single plane, right? So either you take xy plane or you take yz plane or you take xz plane. So it is possible to define the motion of all the links in a single plane only. So this is generally referred to as planar mechanism. Now let us calculate the degree of freedom, right? So first of all, for a mechanism, very important, for a mechanism, we know that one link is fixed, right? So just tell me here, for a mechanism, one link is fixed, correct? So let me take this as a mechanism. So I fixed just one link. So how many links are now free to move? Just tell me. So n is the total number of links, right? So how many links they are free to move now? N minus 1, very obvious. Now just tell me, one link, a single link, it has how many degrees of freedom?
1.
One.
Okay, so let me tell this more clearly. Let me consider this link, right? Now this link, it will have how many degrees of freedom? Let's say I remove these constraints right now. Let's say I remove all these constraints. So let's say this is your xy coordinate and there is only one link lying here. No other link is lying here.
3, sir.
3, very good. So in this case, if you remove, let's say like for a moment, all these constraints. So now in this case, you observe here that it is possible that this link is going to translate, and at the same time it is possible in the x direction, and at the same time it is possible that this link, it may translate in the y direction. And again, there could be a possible rotation of this link, right? Theta, let us say. So now one link, it will have 3 degrees of freedom, right? So out of this, there will be 2 translational, or you can say 2 translatory and 1 rotational, right? So now if one link, it has 3 degree of freedom and n minus 1 links are free to move. So what will be the degree of freedom for this?
3n minus 3.
N minus 1, right? Or you can simply say 3 multiplied by n minus 1. So one link is having 3 degree of freedom. So n minus 1 links, they will have 3 multiplied by n minus 1 degrees of freedom. Now we are going to put the constraints, right? So let us say if we have j revolute pairs, let us say simply revolute or prismatic pair, right? So now come here. So one revolute pair, R pair or P pair, right? It allows 1 degree of freedom, right? Correct. So you might have seen when we discuss kinematic pairs that if there is a revolute or a prismatic pair, it will just allow only 1 degree of freedom. So that means 2 degrees of freedom, 2 degrees of freedom are arrested. Fine. So 2 degrees of freedom are restrained or arrested, right? So if 2 degrees of freedom are arrested, then just tell me now the degree of freedom of the mechanism, it should be equal to 3n minus 1, right? So this was the situation when all the links, they were free to move in the xy plane, right? But now what we did, we started connecting these links by simple hinges, or let's say revolute or prismatic pair, and we know that a revolute pair or a prismatic pair, it will allow only 1 degree of freedom. So let me say this. Let's say if I connected these two links, right? So by this revolute or turning pair, so we know that this link 1, it is going to have only relative motion with respect to link 2, right? So we will need only one coordinate. Oh, I'm sorry. Okay, so we will need only one coordinate theta, right, to simply represent the motion between these two links 1 and 2. That means only 1 degree of freedom is allowed, 2 are arrested. Now these two links, they cannot either translate in x or y direction, correct? So just tell me what will be the degree of freedom of mechanism now?
N
3n,
minus 1.
yeah, minus
N minus 1.
3n minus 1 minus, oh my god. I don't know whether it will be saved or not.
I want to understand why.
Just a minute. Let us try to respond. Okay, will it be saved automatically or not?
I think no, sir.
Okay, so let me then just discuss this in this way. So it will be C. 3n minus 1 degrees of freedom were there, and 2 degrees of freedom, they were being arrested for a single revolute pair. So if there are j revolute pairs, so I think 2j degrees of freedom will be arrested. So now the degree of freedom will be simply, right, 3n minus 1 minus 2j. So that will be the new relation. So okay, for today then let us stop here. Okay, so maybe we will discuss this thing later on in the next session. Fine, because I think like it's very important to save this PPT. Okay, so till now, till this point, any other doubt?
Sir, when you are going to upload these videos?
So by the end of this week, I will do all these things, right? So last night also I got a query, I think from Shrey, and one more student was there. So by the end of this week, I will upload the PPT and the video both, right?
Sir, you will upload a PPT in LMS?
No. I will do it on some Google Drive folder, right? So because LMS sometimes it takes a lot of time to upload there, right? So I will upload on, let's say, like G Drive or Google Drive.
Okay.
Okay. So anything else?
Sir, can you share the PDF for the 5th edition textbook?
I will check. See if there is no problem, even if you refer to the 3rd edition, right? And anyways, I am providing you this PPTs. So even if you go through this PPTs, right? So I think you will be able to cover the entire syllabus. So there is no issue, even if you refer to the 3rd edition, even if the PDF for 5th edition is not available, right? So 3rd
Okay, sir.
edition, there is not too much difference between these two. I think I need to close the program. So If let's say like is the presentation is saved, then it's good luck for all of you. If it is not saved, then I think I will share some.
The
let's say,
recording is there, right? So
The recording
we'll
is there,
refer
no?
to it.
Yes, sir. Recording is there. Sir.
Okay, then fine. Let me end this meeting. The degree of freedom part we will discuss later on. Okay. So thank you all of you.
Thank you, sir.
Thank you.
Thank you.
Thank you, sir.